Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, we started working on creating render items and we got pretty far in the implementation. The only major part that's left to do is the creation of unique pipeline state objects, or PSOs, for our render items. In this video, we are going to look at how these PSOs are created and shared between render items. Let's have a look at an example of how we are creating PSOs in the renderer. In the Gpass module, we can see that we use a stream of pipeline state sub-objects to create the pipeline with the values that we set for each sub-object. In this case, we are setting the values only for sub-objects that are relevant for this render pass. Now we need to create a pipeline state in order to render a submesh. As we saw in the previous video, we create one render item for each submesh, and each render item refers to a pipeline state that is used for rendering. That, however, doesn't mean that we need to create one pipeline state for each render item. As long as submeshes are rendered using the same set of shaders and other relevant pipeline settings, the same pipeline state can be used for rendering. Now, because we are going to set most of pipeline sub-objects, I'm going to add a new helper class that bundles nearly all possible sub-object classes together so that we don't have to define our local stream structure every time we want to create a pipeline state object. Here we can also set default values for each sub-object. We haven't defined any blend state helpers yet, so let's skip this for now. I'll define blend states in a minute. We do have rasterizer states defined, so I can set this default value to no call, which means that both front face and back face triangles are going to be rasterized. We are using depth stencil 1 sub-objects instead of depth stencil, so I'm going to remove this one. Sampler's default is 1 sample with quality set to 0. Depth state is disabled by default, and that's it pretty much for this helper class. Next, let me define a few more depth states. Until now we didn't need depth because all we did was draw a full screen triangle, but now we need depth information to do proper 3D rendering. And while I'm at it, I'll also add a read-only depth state, which we'll use to only read from the depth buffer during the Gpass. Soon we are also going to use reversed depth in order to improve depth precision, and therefore we need reversed and reversed read-only depth states. Again, I'll explain more about these at the time when we are going to use them. For now, we are interested in these 3 fields. The first one enables depth stencil feature, and the second one determines if writing to depth buffer is allowed. For read-only depth, we set this to mask 0. And finally, the comparison function is used to determine which values in the depth buffer should be overwritten by the current value. For normal depth buffers, where the minimum depth is 0 and maximum depth is 1, any pixel that's closer to the camera will overwrite the old value. Close to the camera means a smaller depth value, and therefore the comparison function is set to less than or equal. For reversed depth buffer, the depth range is reversed and objects closer to the camera have a greater depth value. That's why the comparison function for reversed depth is set to greater than or equal. Now on to blend states. Because at this point we are only supporting opaque materials without blending, we just need a state that disables blending. However, I'm also going to quickly put together some other blend states just to give an example of what kinds of blend states we can have. I'm going to rush through this because blend states deserve a bit of proper explaining, and I'd like to do that in another video where we are going to actually use blending. In short, a blend state is a way of defining how the pixel color that was determined in the pixel shader will be written to the render target. In Direct 3D, up to 8 render targets can be written to by a pixel shader simultaneously. That means that one blend state can be defined for each render target independently. If we only have one render target or simply want the same blend state to be applied to all render targets, we can disable independent blend states by setting this field to 0. When independent blending is disabled, only the state of the first render target will be used. As I mentioned, we can define how the new pixel color is written to the render target. When blending is disabled, the new color simply overwrites any old pixel color that might already exist on the render target. This is a setting we want for fully opaque objects. While we are here, I'm also going to add some other blend states that we might need later. I'm not paying much attention to setting these fields correctly, and they might very well be wrong, but I'll explain them if and when we need them, and correct any mistakes I'm making now. As an example, we are going to need alpha blending for objects that have translucent or transparent parts. Now that we have some blend states defined, we can set the pipeline subobject for blend states to be disabled by default. This helper class is now ready to be used in our pipeline state creation function. Because we are going to create 2 pipeline states, one for depth prepass and one for Gpass, I'm going to add a struct that can hold a pair of PSO IDs. Then we can write a function that returns a pair of IDs. These could be the IDs of already existing or newly created PSOs. Because materials contain information about which shaders should be used to render an object with a particular material, we need to pass the material ID. We also need the primitive topology type in order to create a PSO. As you already may know, we have different vertex element formats, which we need to take into consideration as well. In this video, we are not going to bother with vertex formats yet, but I'm adding the elements type as a function parameter anyway. We lock material data before reading material information. In order to decide if we need to create a new pipeline state object, we fill in the pipeline subobject stream class that we just wrote and check if we already have had a pipeline state object stream with the exact same contents. In that case, we would know that a pipeline state object already exists that matches our current stream. Obviously, we don't want to keep every single stream around in order to compare them with the current one. That would be a waste of memory and CPU resources. However, we can compute a hashcode for the current pipeline subobject stream. If a hashcode with the same value already exists, we can use it as a key to acquire the ID of an existing PSO. To calculate the hash, I'm going to use an intrinsic function for cyclic redundancy check, also known as CRC32. These are functions that take up to 8 bytes and compute the CRC value for the data in those bytes. Of course, most of the time our data is larger than 8 bytes, so we need to feed it into this function in chunks of 8 bytes and use the CRC of the previous 8 bytes to compute a new CRC value. We repeat this process until we reach the end of our data buffer. For this to work, we need to align our data size up to 8 bytes. That means that we might end up with some unused space at the end of the buffer where we place our pipeline subobject stream, which is fine as long as we fill the unused bytes with zeros. As I just explained, we need a buffer for the pipeline subobject stream with a size that's a multiple of 8. So we can calculate this size and allocate a buffer with that size on the stack. Then we can construct the stream inside that buffer using placement new. Before doing so, we make sure that any unused bytes in the buffer are set to 0 by zeroing the entire buffer. Now we can dereference the pointer and start filling in the stream. First, we fill in the render target format array, where we need access to the Gpass main buffer format. Therefore, I'm going to take both main buffer and depth buffer format constants out of the CPP file and make them accessible in the Gpass header. After setting render target format array, we use material stream to find and set the root signature pointer. Next, we need to get the primitive topology type from primitive topology. The topology type is just a classification of the primitive topology. It's simply whether our primitive is a point, a line, a triangle, or a patch. This can be done using a switch statement, which I'll put in a separate function. We use the Gpass depth buffer format for depth stencil format, set the rasterizer state to backface culling, and the depth state to enabled read-only. This is because the current stream is for the Gpass, which comes after the depth prepass, so we don't want to write to the depth buffer. We also disable blending and move on to shaders. We use the shader flags and shader IDs from the material to get the bytecode for the shaders. Then we set all shader sub-objects in the stream, regardless of whether or not they are used for this material. The shader stages that are not used have no pointers for their bytecode. This is everything that we need to fill in the stream in order to create a PSO for Gpass. As I explained earlier, creating a new PSO might not be needed, and in order to determine that, I'm going to write another function that creates a PSO only if needed. We can also create the PSO for the depth prepass, and that's done by removing the pixel shader and setting the depth state to enabled. We put both IDs in the PSO ID pair and return them. Let's write this function next. It takes the buffer pointer to the stream and its aligned size to create a PSO. In addition, we also have a parameter that's used for naming the PSO depending on whether it's for Gpass or depth prepass. And since it's only for debugging, I'll mark it as maybe unused. In this function, we are going to compute the hash code for the current subobject stream using the crc32 intrinsic function. Therefore, I need to write a utility function that computes the crc value for the entire buffer. This is a fairly simple function that reads the data in chunks of 8 bytes and feeds them into the intrinsic function. Note that any bytes that don't fit in an 8-byte alignment are ignored, and therefore this function might return the same value for different data if they happen to be the same except for those ignored bytes. That's why we aligned up the buffer size for the pipeline subobject stream. After calculating this key, we can use it to try and find a PSO ID. If we find such an ID, we are done and we can return it. If we didn't find a value for this key, that means that we need to create a new pipeline state. So we cast the stream pointer to a subobject stream pointer type and use it to create a pipeline state. Then we add the pipeline state pointer to the array of pipeline states. We also give the newly created pipeline state object a name. Finally, we add the ID to the PSO map using this key and return the ID. Obviously, we don't need to add the ID again if it already existed, so let's fix the code to return the found ID immediately. I believe this is all for creating Gpass PSOs, so now we can call this function to get the PSO IDs when we are creating a low-level render item. Building the project gives a couple of warnings. This one is a bug. I need to give this lock variable a name, otherwise it will unlock right away. Elements type is on reference for now, but we are going to use it in a future video. In order to create and remove render items, we need to add a couple of functions in the high-level renderer. These have the same signatures as the functions that we wrote for the low-level renderer. We need to expand the renderer interface so that we can call the low-level functions. Then we can set the function pointers and call them in the high-level renderer. So I think we have enough to create a render item for the geometry asset which is loaded in our test application. We have the geometry ID, and we need to provide an array of material IDs with one material for each submesh. Oh, I forgot to call the low-level render item functions. Let's do that first. Looking at the model that we are loading, we can see that it consists of 5 submeshes. Therefore, we need 5 material IDs in order to create the render item. Of course, we don't have to use 5 different materials, and we can use the same material ID for all submeshes. This should be enough to create a render item. Running the code, we get a failed assertion because I used an invalid ID for the game entity. I'm going to turn it off for now to test the code. Now I just step through the code and see if the data makes sense and we are not getting any strange values. Trying to create a pipeline state, we get an error which says that the geometry shader profile is wrong, which is weird because we are not using a geometry shader. Let's try again. Okay, where we set our shaders, I used the wrong order of indexing into the array, which is now trying to set the pixel shader for the geometry stage. So that error message makes sense now. Let me fix it quickly and try again. Now we can see that creating PSOs for both Gpass and depth prepass was successful. In addition, we can see that only 2 PSOs were created for our 5 submeshes, which means that creating unique PSOs using hash codes also works correctly. And we can see that 5 render items were created for this geometry. When closing the application, we get a failed assertion about a free list that's not completely empty. Ah, I see. We need to remove the render items when we close the application, which I forgot to do. So let's do that now and see if it helps. I also put back the assertion for entity and geometry IDs and just use 0 because we are not doing anything with the entity right now, so it should be fine. That's it for this episode. Next time we are going to write a constant buffer class to manage sending data to shaders. We need this, for example, to send view and projection matrices, as well as model to world transform matrices for each object to the GPU. As always, thank you so much for joining me today, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!